Hello AP Chem students and welcome to topic 6.6, Introduction to Enthalpy of a Reaction. The learning objective for today is 6.6.a, calculate the heat Q absorbed or released by a system undergoing a chemical reaction in relationship to the amount of the reacting substance in moles and the molar enthalpy of reaction. So let's look at it. So enthalpy is the total heat content of a system. Because most of the reactions we will consider are happening at constant pressure, we are going to assume that the enthalpy for the system is the same as the internal energy, which is the total energy contained within a system for that system. This is not actually tested on the AP chemistry exam, but I think enthalpy makes a little bit more sense if you know what internal energy is. So we're just scratching the surface with a real quick definition here. So the external kinetic energy is the energy associated with the overall motion of an object. The internal kinetic energy is the energy associated with the random motion of the particles within the object itself. So first of all, enthalpy is an intensive property, which means that it does not matter how much of the substance you have. It has unique values, though, that are affected by the state of a substance. The reason enthalpy is intensive is because we measure it per mole. So then that makes it intensive. We cannot measure enthalpy directly. We can only measure the change in enthalpy. So your delta H is equal to your enthalpy of your products minus your enthalpy of your reactants. Okay, so there you go. So if you did not measure it per mole, then it would be an extensive property, but we report it per mole, so then it's intensive. So the chemical potential energy of the products of a reaction is different than that of the reactants because of the breaking and forming of bonds. And so you can see that down here on the graph. So really important that you know energy is required to break bonds and energy is released when you form bonds. If you have taken biology, you might have heard something different. Biologists approach the concept of breaking and forming bonds differently than chemists do, and therefore that leads them to have a different classification. But this is true. Energy is required to break bonds. Energy is released when you form bonds. We are looking at bonds specifically on an individual basis, breaking and forming those bonds. When you're talking about it in biology, you tend to look at an overall process. And so they do different things in chemistry. When we're talking about chemistry, energy is required to break bonds. Energy is released when you form bonds. Really important that you keep that in mind moving forward because that will help you think about the signs and whether systems are endothermic or exothermic from all points here on. So the energy difference results in a change in the kinetic energy of the particles, which manifest as a temperature change. When enthalpy is given for a reaction, that value can be used as a conversion factor using coefficients of ratios, which is really just an application of stoichiometry. So if we examine this reaction here, where you can see the synthesis of nitrogen dioxide from its elements, this has an overall delta H of plus 68. I have lost my mouse. There it is. Okay. And so for this reaction, we can use the following ratios. So your delta H is equal to 68 kilojoules per 1 mole of N2, 68 kilojoules per 2 moles of O2, and 68 kilojoules per 2 moles of NO2. So again, this is for your overall moles of reaction, if you want to think about it in that way, and then we can use the coefficients individually if we know amounts, like starting amounts for any of the reactants or the products. So let's look at that in terms of a practice. So here's practice 3. What mass of O2 was consumed if 250 kilojoules of heat were produced in the synthesis of NO2 from nitrogen and oxygen? So that's the reaction we just looked at. So I'm going to go through the answer here, so if you want to try it on your own first, pause the video. So as a reminder, here's the reaction that we used, and there's your delta H of plus 68. So we're going to start with 250 kilojoules, and then we're going to set up our little conversion table, and then our enthalpy value will end up on the bottom, which is 68, and then that is kilojoules, and then that is per 2 moles of O2. So then our kilojoules cancel, and then now we were asked what mass of O2 was consumed, and so we can convert from moles of O2 to mass of O2 using molar mass as we typically would. So that's 32 grams per mole, our moles cancel, and then that leaves us with 235.29 grams. But if you look at the original prompt, we were given 3 significant figures here, and actually only 2 significant figures here. Now this is unusual. Normally we would not be given kind of a known value like this to limit our significant figures. So I reported this as 235 but in looking back at the problem, we should actually report this as 240. So let's talk about energy flow. We can get a lot of information about the energy flow between a system and the surroundings from this value. For example, because the sign of the reaction is positive, above, that should say above, not about, is positive, we know that this amount of energy was gained by the system and lost by the surroundings. So gained by the system from the surroundings, if you want to think about it that way. So remember that endothermic has a delta H that is positive and heat is absorbed by the system. Exothermic has a delta H that is negative and heat is released by the system. So we know that this is called an endothermic reaction, that the temperature of the products is lower than that of the surroundings. And the reverse of these things would all be true for a system, for an exothermic system with a negative delta H. So that's it. So what should you be able to do with this? So you should be able to describe the energy exchange between the reaction system and the surroundings by looking at the sign of your delta H given. You should be able to calculate the amount of heat absorbed or released by a reaction by using delta H in a stoichiometric calculation. You should be able to compare and contrast the chemical potential energy of the reactants and products in a system. And that is it. And we are going to be looking at enthalpy more specifically in different situations as we move through the rest of Unit 6. And so I'll see you soon for some more videos on that.